Okay, so let's keep going with the evaluation of this Feynman diagram. So we're simplifying this expression that we got for the denominator. So we get k squared. Then we've got plus 2k dot p1 plus p2 times by x. And then we will have plus p1 plus p2 squared times by x. And then for the minus m squared plus I epsilon, we can see that the x and the minus x cancels. So we just get minus m squared plus I epsilon. Now, what we can do next, and this is a relatively simple step, is that we can complete the square, okay? So this k squared plus the linear term in k can be written as k plus, let's see, it will be x times by p1 plus p2 squared. So if we square this out, we correctly get the k squared. The cross term gives us 2k dot p1 plus p2 times x. But now there is a new quadratic term that we need to subtract off. And this will be minus p1 plus p2 squared times by x squared. So that we need to cancel off. And then we should include the terms that we had before, which is plus p1 plus p2 squared times x minus m squared plus I epsilon. Now, remember, we are integrating d4k. So let's now change variables. Let's change variables to k tilde mu, and k tilde mu will be equal to k mu plus x times by p1 mu plus p2 mu. If we make this change of variables, then because k and k tilde just differ by a constant shift, constant meaning the amount that we're shifting by does not depend on k, that means that d4k will be equal to d4k tilde. So this is a rather trivial change of variables to perform. And in terms of k tilde, what do we have? Okay, so let's put that maybe in brackets. In terms of k tilde, we have k tilde squared plus p1 plus p2 squared x minus x squared minus m squared plus I epsilon. Very good. So now let's see, what does our integral look like? We can return to the integral. So I will be equal to 288 g squared z squared. We'll have the integral over the Feynman parameter from 0 to 1 dx. Then we will have an integral d4. Now it will be k tilde. And then the integrand is 1 over, and we will have k tilde squared plus p1 plus p2 squared into x minus x squared minus m squared plus I epsilon, and this is squared. Okay, so let's make a few comments now. So first of all, by adding the denominators, so remember, we had a product of denominators, a times b. The Feynman trick let us write this as a linear combination of a and b with coefficients x and 1 minus x. But by adding these two denominators, we were able to complete the square, and the integrand now is just a function of k tilde squared. Well, that simplifies things a lot, that the integrand depends only on k tilde squared, and it's because of this that we are going to be able to do this integral over the momenta. And this is what the Feynman trick did for us. So let's maybe just summarize that. So the Feynman trick, so you might wonder, why did we do the Feynman trick? Well, the Feynman trick lets us, it implies dependence only on k squared. So that's why the Feynman trick is actually useful. And that's great, you know. In general, this will be a very general conclusion. You will always find that the integrand depends only on k squared. And in fact, the integrand will always take a very similar form. So that's the first comment I wanted to make. The second comment I wanted to make, and this is where you really start to see something typical of quantum field theory, is that this integral is divergent. So we now start to see, so this integral is divergent. We now start to see some of the divergences that start to appear in quantum field theory. And to see that this integral is divergent, I want to study an integral of this form. So let's study an integral d4 k tilde, and then we'll have 1 over k tilde squared plus delta squared. Okay, so how does this differ from the integral above? Well, I've dropped the integral of the Feynman parameters. Well, that's an integral over a finite interval. That's certainly not going to affect whether it's divergent or not. And then we've got the 288g squared z squared. Well, that's just a constant multiplying it. And then I've got the integral d4k, just like I did above. Oh, this integral over here should have been over 2 pi to the 4. So that's important. I shouldn't drop that. And I'm not going to bother about the 1 over 2 pi to the 4 here, though. And then I've got an integral I've written as k tilde squared plus delta squared. In actual fact, this last integral that I wrote down, this is going to be the form of practically all of the integrals that you consider. The only things that could change is maybe this 2 will be some other power, and maybe the specific form of delta will change. But this is always the structure of the integral that we have to perform, and we're going to get a general formula for this integral. Now, it really doesn't matter if I call my integration variable k or k tilde. So I'm just going to remove the tildes, okay? I'm just going to call it d4k. Good. Okay, so now let's study this integral. And we want to show that this integral is divergent. That will illustrate for you the divergence that I'm talking about. So we can split this into an integral over the spatial momenta. This will be d3k over all of the spatial momenta. And then we've also got an integral over dk naught. And if I write out exactly what this integrand is, it's 1 over k naught squared minus k dot k, and then we've got plus delta, and this is squared. Now, this is such a pity that we've got k naught squared minus k dot k. You see, if we had a normal dot product, really a k dot k with a 4-dimensional vector, then we could easily have changed to a radius and some angles, and the integral over all of the angles would have been trivial. But unfortunately, we've got k naught squared minus k dot k. So what we would like to do, what we're going to try to do now is we're going to change the sign of the k naught squared term. And again, that's so that we can then, for this 4-dimensional vector of the momenta, after we've changed the sign of k naught squared, then actually we can change to a radius and angles in 4 dimensions, and the integral over the angles becomes trivial. So how are we going to change the sign of k naught squared? We can't just change the problem. So we have to rewrite this problem without changing the value of the integral. Well, we're again going to make use of complex analysis. So let's take a look now, and we're going to look at the complex k naught plane, okay? And what is our integration contour? Well, we are integrating from minus infinity to plus infinity over this red contour. So let's call that maybe, I don't know, C1. And you know, in fact, that there are poles in the complex k naught plane. We've studied those poles and we've looked at them. inside delta, there is a plus I epsilon. So this plus I epsilon is going to shift the poles in exactly the way that you've already seen it when we studied the Green's function in detail. So what happens? There's a pole at some positive k naught, and that gets shifted slightly down. So this is where one of the poles sits. It's just below the axis. There's another pole sitting at a negative k naught, just above the axis. What I am going to claim now is that we can freely deform the contour to this contour C2. So I'll lay the path here. This portion of the path that is curved, you should think about that portion of the path all living at infinite values of the momentum k naught. Then I'll go up the axis over here. So I'll be integrating along the imaginary axis, and then I will come down the axis over here to infinity. And again, all of the curved portions of the path are at the mod of k naught is equal to infinity. This is the complex k naught plane. And when we deform the path like this smoothly, you can see that we did not move the contour through any poles. And in fact, the general statement in complex analysis is that you don't change the value of the integral if you deform the path in such a way that you don't go through any poles. Okay, so the first thing that I'd like to do, so the first thing we'll do, so number one, let's prove that the integral along C1 is equal to the integral along C2. So if I do the integral using contour C1, I'll get exactly the same answer as if I integrate using the contour C2. Good. We will do that in a moment.